Imagine this. Somewhere in the universe right now, at this very moment, there's a place where time itself breaks down, where clocks run backwards, where yesterday and tomorrow become meaningless words, where the very fabric of reality tears open like wet paper. A place so extreme that if you venture too close, you could watch the entire future of the universe unfold in moments, or become frozen in time for eternity, depending on your perspective. This isn't science fiction. This isn't a Hollywood fantasy. This is science fact, happening right now, in thousands of locations scattered across our cosmos. And these cosmic monsters, black holes, might just hold the key to humanity's oldest, most persistent dream, the ability to travel through time. The mystery begins. Conversational, engaging time travel. Just saying those words conjures up a cascade of images and possibilities, doesn't it? We've all dreamed about it. Going back to fix that embarrassing moment in high school when you said exactly the wrong thing. Jumping forward to see if humanity finally achieves interstellar travel. Meeting your great-great-grandchildren and seeing what kind of world they inherit. Witnessing the construction of the pyramids, or watching the first humans set foot on Mars. The fantasy of time travel has captivated human imagination for as long as we've been able to conceive of time as something more than just sunrise and sunset. It appears everywhere in our culture, from H.G. Wells' pioneering novel The Time Machine, written in 1895, to modern blockbusters like Back to the Future, Interstellar, and Avengers: Endgame. Philosophers have pondered it for millennia. Physicists have theorized about it for over a century. And dreamers? Well, dreamers have wished for it since the dawn of human consciousness. But here's what most people don't realize, what gets lost in the Hollywood spectacle and the science fiction novels. The universe has already built time machines. They're operating right now. They've been working for billions of years, bending and twisting the very fabric of time in ways that would make even the wildest science fiction writer pause, double-check their notes, and say, wait, that's actually possible? These time machines are called black holes, and the more we learn about them, the more we realize that time, that thing we think we understand because we've experienced it every single day of our lives, is far, far stranger than we ever imagined. What makes black holes so special? Educational, building intrigue. Let's start at the beginning, with what a black hole actually is, because I promise you, it's so much stranger and more wonderful than most people think. A black hole isn't really a hole at all. That's the first misconception to clear up. It's not a tunnel or a doorway or an empty void in space. A black hole is what happens when something incredibly massive, like a star 20 or 30 times bigger than our sun, reaches the end of its life and dies in one of the most spectacular events in the universe, a supernova explosion. Here's how it happens. For millions or even billions of years, a massive star has been in a delicate balance. The crushing force of gravity, trying to squeeze all that stellar mass into an infinitely small point, is perfectly counterbalanced by the outward pressure from nuclear fusion in the star's core, the same fusion that makes the star shine. It's like an eternal tug-of-war, with the star's mass pulling inward and the energy from fusion pushing outward. As long as the star has fuel, this balance holds. But eventually, inevitably, the star runs out of fuel. The nuclear fusion stops, and suddenly there's nothing to counteract gravity anymore. What happens next occurs in less than a second, but it's one of the most violent events in the cosmos. The star's core collapses. We're talking about something with the mass of several suns getting compressed into a space the size of a city, then smaller still. The outer layers of the star rebound off the collapsing core and explode outward in a supernova that can briefly outshine an entire galaxy of hundreds of billions of stars. But that's not even the most dramatic part. The core keeps collapsing, down past the size of a city, past the size of a mountain, smaller and smaller, denser and denser, until, according to our best theories, all that mass gets compressed into a point of literally zero volume, a mathematical singularity where density becomes infinite. The result? Gravity so intense, so overwhelmingly powerful, that it doesn't just pull on objects, it warps the very structure of space and time itself. It tears a hole in reality. The event horizon. Sense of awe and mystery. Around every black hole exists what we call the event horizon. The name sounds poetic, and it is, but it's also deeply descriptive. It's the ultimate point of no return, the boundary where the escape velocity exceeds the speed of light. Cross that line, and not even light itself, the fastest thing in the universe, travelling at 186,000 miles per second, can escape. That's why we call them black holes. No light escapes, so they appear as perfect darkness against the cosmic background. But here's the absolutely mind-bending part, the thing that most people don't fully grasp. The event horizon isn't just a spatial boundary. It's not just a place in space. It's a temporal boundary too. It's a place where time itself behaves so strangely that our normal concepts of past, present, and future completely break down. Think about that for a moment. We're not just talking about a place where gravity is strong. We're talking about a place where time, that fundamental dimension of reality that we all experience moment by moment, fundamentally changes its behavior. To understand how black holes could help us comprehend time travel, we first need to shatter a common misconception that almost everyone carries around without even realizing it. Time isn't what you think it is. Mind-expanding, revelatory tone. You probably imagine time as this universal clock, ticking away at exactly the same rate whether you're on Earth, on Mars, on a planet orbiting a distant star, or floating in the emptiest void of intergalactic space. A second is a second is a second, everywhere and always. Right? Wrong. Spectacularly, fundamentally, provably wrong. This was Albert Einstein's great revelation, the insight that revolutionized physics and earned him a place among the greatest scientific minds in history. In 1905, he published his special theory of relativity, which showed that time is relative. It flows at different rates depending on how fast you're moving. Then, in 1915, he followed up with his general theory of relativity, which revealed something even more profound. Gravity doesn't just pull on objects. Gravity is the warping of space-time itself. And strong gravitational fields don't just curve space, they slow down time. Let me repeat that because it's crucial. Time runs at different rates depending on where you are and how you're moving. This isn't philosophical speculation or abstract mathematical games. This is hard, tested, verified physics. We can measure it. We have measured it thousands of times with increasing precision. Consider GPS satellites. These satellites orbit about 12,500 miles above Earth's surface, travelling at speeds of roughly 8,700 miles per hour. Up there, they experience both effects Einstein predicted. Time runs slightly faster because they are in a weaker gravitational field than we experience on Earth's surface, about 45 microseconds per day faster. But it also runs slightly slower because they're moving so fast relative to us on the ground, about 7 microseconds per day slower. The net effect is that time runs about 38 microseconds per day faster on the satellites than on Earth. That might sound trivial, 38 millionths of a second per day. But GPS works by measuring the time it takes for signals to travel from satellites to your phone. Light travels about 1 foot per nanosecond, so 38 microseconds translates to about 11,400 meters, more than 7 miles. If GPS satellites didn't account for time dilation, your navigation would be off by miles within hours, and the system would be completely useless within days. Every time you use GPS to navigate to a restaurant or find your way home, you're relying on Einstein's theories of relativity. You're using time travel physics just to find the nearest coffee shop. Or consider the astronauts aboard the International Space Station. They're orbiting Earth at about 17,500 miles per hour, roughly 250 miles up. Because of their speed and the slightly weaker gravity they experience, they age microseconds slower than people on Earth's surface. It's a tiny effect. Astronaut Scott Kelly spent a year in space and came back about 8.6 milliseconds younger than he would have been if he'd stayed on Earth. But it's real, measurable, and it proves that time is not the fixed, universal thing we intuitively believe it to be. Now, imagine what happens when you're not dealing with Earth's relatively gentle gravity or the modest speeds of satellites and space stations. Imagine what happens near something with gravity millions, billions, or even trillions of times stronger than Earth. Near a black hole, time doesn't just slow down a tiny bit. It goes absolutely, mind-bendingly haywire. The time machine you can't escape. Dramatic, building tension. Here's where black holes transform from merely fascinating cosmic objects into nature's ultimate demonstration of time's malleability. Actual, functioning time machines. Let's conduct a thought experiment. Imagine you have a friend, let's call her Sarah, who's brave, curious, and perhaps a bit reckless. Sarah volunteers to approach a black hole while you remain at a safe distance in a spaceship, watching through a powerful telescope. She's wearing a bright suit with flashing lights so you can track her easily, and she's sending you a constant video feed. As Sarah begins her descent toward the black hole, at first everything seems normal. She waves, you wave back. The radio communication is clear. She's falling faster and faster as the black hole's gravity accelerates her downward. But then, as she gets closer to the event horizon, you start noticing something strange. Her movements seem to be slowing down. At first you think maybe it's just the video feed lagging, but no, it's something else entirely. She's moving in slow motion, as if someone is gradually turning down the playback speed of reality itself. Her wave takes longer and longer to complete. Words from her radio transmission start to stretch out, her voice dropping to a lower pitch as the sound waves get elongated. The flashing lights on her suit blink slower and slower. Colours begin to shift toward red as the light from her body gets red-shifted, stretched to longer wavelengths by the intense gravitational field. Eventually, from your perspective as the distant observer, Sarah appears to move slower and slower and slower, asymptotically approaching zero. She gets closer and closer to the event horizon, but never quite seems to reach it. Her image becomes increasingly redshifted, darker, dimmer. Time, from your perspective, appears to nearly stop for her right at the event horizon. If you waited, and you'd have to wait an infinitely long time, you'd never see her cross that boundary. From your external vantage point, Sarah would appear to be frozen at the event horizon forever, a slowly fading image suspended in time until the universe itself ends. But here's where it gets truly bizarre, where the real, mind-bending nature of relativity comes into play. Sarah's experience would be completely different. From her perspective, from her frame of reference, time would feel totally normal. She's not experiencing anything slowing down. Her watch ticks at its regular pace. Her heartbeat feels normal. Her thoughts flow at their usual speed. She would cross the event horizon in finite time, maybe seconds, maybe minutes, depending on the size of the black hole and her trajectory. There would be no magical barrier, no invisible wall, no moment where she thinks, "Aha! This is the event horizon." She'd just keep falling. In fact, for a supermassive black hole, the kind that lurks at the centres of galaxies, with masses billions of times that of our Sun, she might not feel anything special at the event horizon at all. The tidal forces could be quite gentle. She'd cross the point of no return without even noticing it, only realizing she was doomed when she tried to escape and found it impossible. This is the fundamental paradox at the heart of black holes. Time depends entirely, completely, utterly on perspective. There is no absolute, universal now that applies everywhere. Your now and Sarah's now have diverged so dramatically that they've essentially become different realities. Forward through time, the realistic time machine, excitement building, possibilities opening. Now we arrive at the part that should excite anyone who's ever dreamed of time travel, because this is where the fantasy starts to become, at least theoretically, achievable physics. If you wanted to travel to Earth's far future, say, 10,000 years from now, or 100,000 years, or even millions of years, a black hole could theoretically get you there. Not through magic or wormholes or anything exotic, just through good old-fashioned time dilation, the same effect that makes GPS satellites age differently than ground stations, just taken to its absolute extreme. Here's the recipe. First, you'd need a spacecraft capable of travelling to a black hole, and crucially, capable of escaping from close proximity to one. That alone requires technology far beyond what we currently possess. We're talking about engines that can generate enormous amounts of thrust to fight against gravitational forces that dwarf anything in our solar system. Next, you'd need to orbit close to the event horizon of the black hole. Not so close that you cross it. Remember, there's no coming back from that. But close enough that time dilation becomes extreme. The closer you get, the more dramatic the effect. Let's say you orbit at a distance where time runs, from an external perspective, at 1/10 the normal rate. You spend what feels like 1 year orbiting the black hole. You read books, exercise, eat meals, sleep. Everything feels completely normal to you. Then you fire up your engines and escape back to Earth. You've aged 1 year. Your spacecraft's. Clock shows 1 year has passed. But when you arrive home, you discover that 10 years have passed on Earth. Your family and friends are a decade older. Technology has advanced. Politics have shifted. A decade of history has unfolded while you experienced a single year. Want to go further into the future? Orbit closer to the event horizon, where time dilation is more extreme. At the right distance, you could orbit for what feels like a few weeks, and return to find centuries or millennia have passed on Earth. This isn't speculation. This isn't theoretical fantasy that might be disproven tomorrow. The physics is rock solid, built on general relativity, a theory that has passed every experimental test thrown at it for over a century. Time dilation near massive objects is a confirmed, verified, undeniable prediction of how our universe works. In Christopher Nolan's 2014 film Interstellar, there's a memorable scene that, while dramatized for cinema, is based on real science. The characters visit a planet orbiting extremely close to a supermassive black hole called Gargantua. They spend what feels like a few hours on the planet's surface, dealing with massive tidal waves. When they return to their spacecraft, they discover that over 23 years have passed for their colleague who remained in orbit. The astronaut who stayed behind has aged more than 2 decades, while his friends aged only a few hours. The filmmakers worked with physicist Kip Thorne, who won the Nobel Prize in 2017 for his work on gravitational waves, to ensure the time dilation in the movie was scientifically accurate. The proportions are correct. The physics checks out. If such a planet existed in such an orbit, that's exactly what would happen. So forward time travel via black holes isn't just possible, it's practically guaranteed by the laws of physics as we understand them. The only thing stopping us is engineering. Building spacecraft that can reach black holes. The nearest known black hole is over 1,500 light-years away, and survive the intense gravitational forces near the event horizon. But those are technological challenges, not fundamental impossibilities. Given enough time, enough resources, enough ingenuity, humanity might one day, the ultimate question, can we go back? Mysterious, speculative tone. Forward time travel via black holes is theoretically possible, practically challenging, but fundamentally allowed by physics. But what about the Holy Grail? The really juicy question that has obsessed science fiction writers and physicists alike. Travelling backward in time. Can black holes help us visit the past? This is where things get truly speculative, venturing into territory where even theoretical physicists have to tread carefully. But it's also where things get genuinely thrillingly fascinating. The story begins with a New Zealand mathematician named Roy Kerr. In 1963, Kerr found an exact solution to Einstein's equations of general relativity that describes a rotating black hole. This was a major breakthrough because in reality most black holes probably rotate. They form from the collapse of rotating stars, and the conservation of angular momentum means that as the star shrinks, it spins faster and faster, like a figure skater pulling in their arms during a spin. These rotating black holes, called Kerr black holes, have some very peculiar properties that non-rotating black holes don't have. For one thing, they have 2 event horizons, an outer and an inner one. Between these horizons lies a region called the ergosphere, where space-time itself is dragged around the black hole so intensely that nothing can remain stationary. Even light would be swept along in the black hole's rotation. But the truly wild part, the part that gets time travel enthusiasts excited, is this. Some solutions to Einstein's equations for Kerr black holes suggest the existence of closed time-like curves, or CTCs. These are paths through space-time that loop back on themselves. In principle, if you followed one of these curves, you could return to your own past. You could, theoretically, travel in a loop through time and arrive back at the moment you started, or even before you started. The mathematics works. The equations don't forbid it. But, and this is a cosmic-sized but, we have absolutely no idea if these mathematical solutions represent physical reality or are just abstract curiosities that could never actually exist in our universe. There are enormous, perhaps insurmountable problems with backward time travel. The most famous is the grandfather paradox. Suppose you travel back in time and prevent your grandparents from meeting. Then your parents are never born, which means you're never born, which means you can't travel back in time to prevent your grandparents from meeting in the first place. It's a logical contradiction, a paradox that seems to break causality, the fundamental principle that causes precede effects. Physicists have proposed various solutions to these paradoxes. Some suggest that quantum mechanics might prevent paradoxes from occurring, that the universe has built-in mechanisms that make it impossible to change the past, even if you can visit it. Others propose the many worlds interpretation. When you travel back and change something, you create an alternate timeline, a parallel universe where the change occurs, but your original timeline remains unchanged. You don't change your past, you create a new branch of reality. Stephen Hawking, one of the greatest physicists of the 20th century, proposed what he called the chronology protection conjecture. It's not a proven theorem, just a conjecture, an educated guess based on intuition about how the universe works. Hawking suggested that the laws of physics conspire, in ways we don't fully understand yet, to prevent backward time travel. Perhaps quantum effects create infinite energy densities that destroy any time machine before it can be used. Perhaps causality is so fundamental to the structure of reality that nature simply doesn't allow it to be violated. The truth is, we don't know. And one of the things that makes black holes so valuable to physics is that they push our theories to their absolute limits, revealing where our understanding breaks down and forcing us to confront these deep, fundamental questions about the nature of time itself. Wormholes. Theoretical shortcuts. Sense of wonder and possibility. Black holes have a theoretical cousin that makes physicists even more excited and more nervous about the possibility of time travel. Wormholes. Imagine space-time as a flat sheet of paper. Your normal journey across the universe means travelling along the paper's surface. If you want to get from one side of the paper to the other, you have to cross all that distance. But what if you could fold the paper so that two distant points touch, then punch a hole through both layers? You'd create a shortcut, a tunnel that connects two far apart regions of space, or perhaps two different times. That's essentially what a wormhole is, a hypothetical tunnel through space-time connecting two distant points. The formal name is an Einstein-Rosen bridge, after Albert Einstein and Nathan Rosen, who first described the concept mathematically in 1935. Some solutions to Einstein's equations suggest that black holes could be one mouth of a wormhole. If you could somehow survive the journey through a black hole, and with current physics you absolutely cannot, but work with me here, you might not end up crushed at the singularity. Instead, you might emerge somewhere else, or someone else. This idea has captured the imagination of science fiction writers for good reason. In Carl Sagan's novel Contact, made into a film starring Jodie Foster, the protagonist travels through a system of wormholes to visit distant parts of the galaxy. Sagan, a trained astronomer and astrophysicist, wanted the science in his novel to be plausible, so he consulted with Kip Thorne at Caltech. Thorne did the calculations and found that, yes, if wormholes could exist and be stabilized, they could theoretically be used for faster-than-light travel and possibly time travel. But here's the catch, and it's a big one. Every analysis of wormholes suggests that if they exist at all, they're probably microscopic, perhaps no larger than subatomic particles. They'd also be wildly, catastrophically unstable. They'd collapse before anything could pass through them, likely in a time frame measured in tiny fractions of a second. Some theoretical work suggests that wormholes might be stabilized using exotic matter with negative energy density, something that pushes outward against gravity rather than being pulled inward by it. We've never detected such matter in any significant quantities in nature. There are some quantum effects that might produce tiny amounts of negative energy, but nowhere near what would be needed to hold open a wormhole large enough for a spacecraft or even a person. So while wormholes are allowed by Einstein's equations, the practical obstacles to using them are staggering. They might not exist at all in nature. If they do exist, they're probably far too small and unstable to use. And if we wanted to create and stabilize one, We'd need exotic matter and energy sources that may be physically impossible. Still, the fact that the equations of general relativity, equations that have proven incredibly accurate in describing how gravity works, don't forbid wormholes is tantalizing. It means we can't rule them out completely. And black holes, as the most extreme gravitational objects we know of, are the most likely places where, if wormholes exist, they might be found. What black holes teach us. Thoughtful, philosophical. Even if we never build a time machine, even if backward time travel proves impossible and wormholes remain forever beyond our technological reach, black holes have already taught us profound, revolutionary lessons about the fundamental nature of time itself. Before Einstein, people thought of time as Isaac Newton described it: absolute, true, and mathematical time, of itself, and from its own nature, flows equably without relation to anything external. Time was the stage on which the universe performed, unchanging and universal. Black holes have obliterated that conception completely. They've shown us that time is not absolute, it's relative, flexible, and intimately connected to space and gravity. They've revealed that the universe is far stranger than our everyday experience suggests, operating on principles that defy common sense, but are nonetheless true. They've demonstrated that our intuitions, shaped by evolution to help us survive on the African savanna, are poor guides to how reality actually works at its most fundamental level. Consider what happens at the event horizon from different perspectives. To an outside observer, an infalling object appears to freeze at the boundary, never quite crossing, its image fading over time. To the infalling observer, they cross the horizon in finite time, experiencing nothing special at the boundary itself. Both perspectives are equally valid. There's no absolute truth about what's really happening. Reality itself is perspective dependent. This isn't just weird, it's revolutionary. It means that the universe doesn't have a single objective now that applies everywhere. Different observers, in different gravitational fields or moving at different speeds, have different nows. The present moment isn't a universal instant, it's a personal local phenomenon. Black holes also force us to confront the limits of our current understanding. At the singularity, the core of a black hole where all the mass is concentrated, our best theories simply stop working. General relativity, which describes gravity and the large-scale structure of space-time, predicts infinite density and infinite curvature. Quantum mechanics, which describes the behavior of matter and energy at the smallest scales, gives contradictory predictions. Both theories are extraordinarily successful in their respective domains. General relativity has passed every test thrown at it, from explaining the orbit of Mercury to predicting gravitational waves. Quantum mechanics underlies all of modern electronics and has been verified to extraordinary precision. But at the singularity of a black hole, they contradict each other. Something is missing from our understanding. Many physicists believe that the missing piece is a theory of quantum gravity, a framework that unifies general relativity and quantum mechanics, describing how gravity works at the smallest scales. If we can understand what really happens at a black hole singularity, we might finally understand the deepest nature of space, time, and reality itself. We might discover that time isn't fundamental at all, that it emerges from something more basic, just as temperature emerges from the motion of atoms. We might find that at the Planck scale, the smallest possible scale in physics, about 10 to the negative 35 meters, the very concepts of space and time break excitement, cutting-edge science. Today's physicists and astronomers are using black holes as natural laboratories to test our theories about time, gravity, and the fabric of reality itself. And the pace of discovery is accelerating. In April 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole. It showed the supermassive black hole at the center of the galaxy M87, a monster with a mass 6.5 billion times that of our Sun, located about 55 million light-years away. The image showed exactly what general relativity predicted: a bright ring of light surrounding a dark shadow, the black hole's event horizon. In May 2022, the same team released an image of Sagittarius A, the supermassive black hole at the center of our own Milky Way galaxy, just 26,000 light-years away. Our local supermassive black hole, the cosmic anchor around which our entire galaxy orbits. These images aren't just pretty pictures. They're tests of general relativity in the most extreme gravitational conditions we can observe. So far, Einstein's century-old theory has passed with flying colours. The LIGO and Virgo gravitational wave detectors have opened an entirely new way to study black holes. These instruments detect ripples in space-time itself, gravitational waves, produced when black holes merge. In 2015, LIGO made the first direct detection of gravitational waves, confirming a major prediction of general relativity. The signal came from two black holes, 36 and 29 times the mass of the Sun, spiraling together and merging, 1.3 billion light-years away. In a fraction of a second, 3 solar masses worth of energy, that's 3 entire suns, were converted into gravitational waves. For that brief moment, the merger put out more power than all the stars in the observable universe combined. Since then, dozens of black hole mergers have been observed. Each detection provides data about how black holes behave, how space-time responds to extreme gravity, and whether general relativity's predictions hold up in these violent events. Looking forward, planned space-based gravitational wave detectors like LISA, the Laser Interferometer Space Antenna, will be able to detect supermassive black hole mergers across the entire observable universe. These observations will test general relativity in regimes we've never been able to access before. Meanwhile, theoretical physicists are working on the information paradox, developing theories of quantum gravity, and exploring the mathematical structure of space-time near singularities. Some researchers are investigating whether black holes might be connected to dark matter or dark energy, two mysterious components that make up 95% of the universe's total mass energy, but remain poorly understood. Every observation refines our understanding. Every discovery raises new questions. We're in a golden age of black hole physics, with new revelations arriving almost monthly. The human dimension. Intimate. Reflective. There's something deeply human about our fascination with time travel and black holes. It's not just about physics equations and astronomical observations. It's about our relationship with time itself. We are, as far as we know, the only species that fully grasps the concept of time, past, present, and future. We remember what was, experience what is, and anticipate what will be. This awareness of time is both a gift and a burden. It allows us to plan, to learn from history, to imagine possibilities. But it also means we live with regret about the past and anxiety about the future. The dream of time travel is, at its core, a dream of control. Control over our mistakes, control over our fate. The ability to fix what went wrong or see how things turn out. In that sense, time travel fantasies reveal something essential about the human condition. Our desire to transcend our limitations, to be more than creatures trapped in the present moment. Black holes represent the opposite, ultimate lack of control. They're places where we lose all control, where the universe imposes absolute limits. You cannot escape from inside an event horizon, no matter how clever you are, no matter what technology you possess. The laws of physics simply forbid it. Yet even in this surrender of control, there's something profound. Black holes teach us humility. They remind us that we're part of a universe that vastly exceeds our comprehension and our power. They're evidence that reality is more strange, more wonderful, and more unforgiving than our everyday experience suggests. And perhaps that's the most important lesson black holes teach us. The universe is under no obligation to make sense to us. It doesn't care about our intuitions or our comfort. It simply is what it is. And what it is we're discovering is far more extraordinary than any science fiction writer ever dreamed. The ultimate takeaway building to inspirational conclusion. So here's the truth, the conclusion we've been building toward through all this exploration. Black holes won't let us visit ancient Rome or shake hands with our future selves. Not tomorrow, probably not in our lifetimes, and quite possibly never. The engineering challenges aren't just difficult, they're almost incomprehensibly vast. But that's not the point. That was never really the point. The point is that black holes have already shattered everything we thought we knew about time. They've proven that time is not the rigid, unchangeable, universal thing we experience in our daily lives. Time bends, time warps, time can be manipulated. These aren't philosophical speculations, they're verified facts about the universe we inhabit. Time travel to the future isn't science fiction, it's science fact, demonstrated every day by GPS satellites and proven possible in principle by black holes. Think about what this means. Right now, as you listen to these words, there are objects scattered throughout the universe that are literally tearing holes in time. Clocks near them tick at different rates. Futures diverge. Past and present blur together. These aren't fantasies. These are real places, doing real things that would have been considered impossible magic just centuries ago. The next time you look up at the night sky, remember, somewhere out there, billions of light years away, time itself is being stretched, compressed, and twisted into shapes we're only beginning to understand. The universe has already built time machines. They're called black holes, and they've been operating since the first massive stars collapsed billions of years ago. We're just starting to learn how to read what they're telling us, and perhaps, just perhaps, buried in the extreme physics of these cosmic monsters lies the secret we've been searching for all along. Not just how to travel through time, but what time actually is. Black holes don't just bend space-time, they bend our understanding of what's possible. They expand our conception of reality. The universe is stranger, more wonderful and more beautiful than we ever imagined. And the journey to understand it, that journey is just beginning. So stay curious, keep questioning, keep looking up at the stars with wonder. Because the next breakthrough in understanding time might come from someone who never stopped asking, what if? The time machines are out there, scattered across the cosmos, demonstrating truths about the universe that challenge everything we thought we knew. We may never step through a wormhole or orbit an event horizon, but in studying black holes, in grappling with the puzzles they present, we're doing something equally profound. We're learning what it means to exist in a universe where time itself is negotiable. And that knowledge changes us. It expands our minds. It fills us with wonder at the extraordinary universe we're privileged to inhabit and study. Black holes are nature's ultimate teachers about time. And the lesson they're teaching us is this: reality is more amazing than we ever dared to imagine. and we've only just begun to understand it.